Okay, let us continue our course in quantum field theory, and we have a talk by Professor Nahm, who will talk about the automorphic forms and quantum theory.
So, thanks to the organizers for inviting physicists like me in a very interesting paper called Missed Opportunities. Dyson said that because of perturbative quantum field theories, finite diagrams and all that, the happy marriage between mathematics and physics ended in divorce. And, so my talk is about repairing that to some extent. So it's specifically for newcomers to quantum field theory. And the real title should have been on three questions by Don Zagier. So posed some 40 plus years ago. First question, what is quantum field theory? Second question, what are fields? And third question, which actually was asked 45 years ago, why are physicists interested in modular forms? So actually my first contact to Don Zagier was, I came to him and I asked about automorphic forms. He said, that's too big, you should learn about modular forms. And then he gave me a 3-hour lecture on modular forms. So, another part of the talk is the natural generalization of that for certain physical theories. Actually, my first answer when what about QFT, then gave a typical physicist answer. Well, it occurs in nature, and if you know Don, he is interested in very, very many things, but not in nature. So that was the wrong answer. And then for many times, I tried to give better answers, and I always failed. And then last year, the Oberwolfach meeting, it started to improve. So let's see. So first thing you do about quantum field theory, you fix a dimension. And the second thing is you fix a signature, which either may be positive definite, so that's the Euclidean case, or e to the minus 1, the Minkowski case, depending on your state of the mind, the relation is trivial or very deep. So in the first talk we heard today, it's trivial, you replace t by it, so just some analytic continuation. But on the other hand, that gets you from the heat equation to the Schrödinger equation, and they look very similar, just T and IT, but they live in different worlds, and Schrödinger regarded the whole thing as very deep when he invented the Schrödinger equation, because the whole quantum thing comes in, the boundary conditions are difficult, and the whole quantum phenomena are on, most of the quantum phenomena are on this side. But nevertheless, there are these deep relations. And this side, I really don't understand. Both sides occur in nature. This one in solid state physics, for example, at the critical point of water, you have the three-dimensional conformally invariant quantum field theory, and I will talk about Euclidean quantum field theory, which is this side. So for me, a Euclidean quantum field theory is a partition function, and a partition function is a map from some space R to the positive real numbers. You could take logarithms, of course, then it would be just real numbers, but for historical reasons I write it in this way. And then R is space of e-dimensional compact smooth manifolds. with Riemannian metric. If I need a name, manifold M, Riemannian metric G, which prevents me from using G for the genus. So I mainly will talk about the case of d equal 2. D equal 1 is a bit ill-defined or not defined at all, but for my axiom system, it's possible to study the case d equal 1, and it's actually quite illuminating. So this partition function should satisfy 3 axioms, or 4 axioms, 1, 2a, 2b, and 3. And axiom 1 is very simple. Then if you are on a disjoint union, it should be multiplicative. And axiom 2, it should be smooth, and I will explain what that's supposed to mean. In particular, that will be 2a and 2b. And 3, it's a simple property, but I don't quite know how to name it. So I name it very smooth, but I could call it elementary or whatever. So I'll explain it later. Finite depth. If you have a good name, then please tell me. Then I will use that. So smooth means it should admit all possible kinds of derivatives. And so I have to define what do I mean by derivative on a very big space, like that one. And so I want to get all derivatives at once, not by iteration. So let me first look at the case of an affine space. Affine. And then I have vectors which act on A by translation. And then I introduce formal sums of vectors, finite formal sums. So I have a big abelian group. And associate a derivative to it. In the obvious way, I take a limit epsilon to 0 while acting on some function f on A, and then I shift the variable by a vector, and I multiply it by AI, a real number. So you could make it complex, of course, it's real A. And I multiply by a suitable power of epsilon, and I take the limit k to 0. And if this thing is defined and non-trivial, not always 0, then I call that thing the derivative of order k. So, if the whole thing is continuous, then for any vector, of course, k is 0, and the derivative is just 1. And always, if I have 2 combinations here of order k, or maximum k, and I take the derivative, then I get something of higher order. So here, if I have v minus 0, then this is the standard derivative direction v. And well, if I have a big affine space, then I should suppose that d v1 plus v2, well, it should be linear. I don't write it out in detail, of course. Yes. And that gives me one way to have a derivative over here, because the space of Riemannian metrics is locally affine. So I have some just adding some deformations to G. And then I could replace G by G plus epsilon H or so. H some quadratic form on the manifold, and then everything should work here. It should be linear in H, so the derivative with respect to H is the so-called functional derivative. Well, it's linear in H, so you can think about it as a distribution, and if your function is nice and smooth, then the distribution actually can be written as a function, and then it defines a local derivative. So you can take a derivative at points. And so already in the talk of Marianne, then the deep discovery of Einstein was that the energy momentum tensor is really this local derivative with respect to the metric. So deep discovery that there is some in general non-flat metric on our space-time, and when you take derivative with respect to it, then you get the energy momentum tensor. But before I come to that, let me just give some examples. Then also the third question will be answered. So answer to the first question: a Euclidean quantum field theory is a partition function of this kind, which satisfies these three axioms. I have not yet explained the third axiom. Fields are local derivatives, or that would be local fields, but there are also multi-local fields, two local fields, three local fields, and so on, which are defined in the same way. And well, modular forms come up in the examples, and for that reason, I now give you some examples. So first example is Z is determinant suitably regularized of the Laplacian in metric G plus m squared, m some constant, to the power of minus half. That particular quantum field theory is called the theory of a d-dimensional scalar field of mass m. And then you get all the other fields of the theory essentially by taking derivatives, but I've only explained the first method of taking derivatives. So that was the 2a was functional derivatives should exist. So second example, That's the golden ratio model, also called the 2-5 minimal model. Model just means one particular partition function. Minimum model for d equal 2. And then I write it z down for genus 0 and for genus 1. Let me write it first down for genus 1 because the answer is more interesting. Then z of m is the exponent minus where the metric is e to the chi dz bar, where dz is the, well, my manifold is a torus, well, is C divided by 1 état in the usual way, so a torus with coordinate z modulo shifts by the period. So you know what the metric is supposed to be. K is the Gaussian curvature. Z. Based on these ideas, you get differential equations for the Rogers
Let's thank the speaker. So Werner promised to prepare slides today, so probably today in the evening they will appear, and tomorrow you may ask him questions.
After tomorrow, no problem. We can put it later, just after our conference. But it would be nice.
If somebody has a really important question, one question is okay. If not, I will ask. Is this new modular forms, which are not Ziegel as you mentioned, they are related somehow to Riemann theta functions on some lattices, say golden, these Penrose lattices?
There is indeed, but that's a different model. You have theta sums in general non-holomorphic on some lattices. This is an important class of theory, theory of abelian currents. And there one can write down the result explicitly for arbitrary genus, but this is not of that kind. The reason it's not a zeta function in the genus 2 upper half plane, in the interior of it, you have curves with conical singularities. And at this particular locus, I get ramifications of order 5. So I have something which very much looks like a Siegel modular function, but with some extra ramification at a particular locus. So I get something of a 5-fold cover on the Siegel upper half plane. But just 5 functions which degenerate to Rogers or Ramanujan, and which give a 5-dimensional representation of the corresponding modular group.
Okay, thank you, Werner. Let's thank the speaker again, and we start the next talk. It will be now on slides. It's formed up. Please, who is the next speaker? Please come in. It's again a Tanzon. Yes, please. To make it full screen. Control L. Okay. Okay, good. Fine. Okay, it's a talk about formal solutions of the HKP hierarchy.